Again, we're going to go over some new stuff today, and some of you are really going to want to listen up and write this stuff down. You'll see why in just a moment. But we are going to be talking about two-dimensional calculations with forces and Newton's second law. And they're going to look kind of like the warm-up because the warm-up shows forces in two dimensions, both horizontally and vertically. So as I said, I mentioned in the notes a couple times how we would solve this. We just haven't done it together yet. So maybe you remember, maybe not. But the warm-up question for today says, a baseball player bunts. The forces acting on the ball during the time it contacts the bat are shown. What is the net force on the ball? Looking at this, does anybody know how you would find the net force? Sorry? Pythagorean theorem. I told you guys in the notes last week, if you have forces in two dimensions, and maybe some of you did this, if so, awesome. If not, that's okay. We haven't actually done one yet. But I told you that if we had forces in both the x and y directions, that we would have to solve for the resultant force using Pythagorean theorem. It said it in the notes, we just didn't do it yet. Well, it said Pythagorean theorem or trigonometric functions. We're doing both of those today. Okay, so again, these are the forces acting on the ball when it contacts the bat. Find the net force. In order for me to do that, I need to actually redraw these forces in a way that they are drawn head to tail. We talked about vector addition earlier on during Unit 1. And so right now these forces are not drawn head to tail. They're drawn both originating from the object. And I need them to line up so that where one of my vectors ends, the next one begins. That means I could either move my red vector over here, or I can move this blue one down here. Either way, I need to add them head to tail. So I'm going to do it this way. So this one is now head to tail, head of the blue, tail of the red, touching each other. Okay, so we do have to redraw them first and then draw in the resultant. Okay, that's the hypotenuse of a right triangle. So whenever we do this, we're going to be looking at a right triangle, which is how I know that I can solve for that hypotenuse using Pythagorean theorem. Okay, a squared plus b squared equals c squared. I'm going to go ahead and just call, it doesn't really matter which one's a or b, those are just the legs of the triangle. So I did 25 and then 3, but if you did it the other way, you're going to get the same answer. 25 squared plus 3 squared equals c squared. That's 625 plus 9 equals c squared. Okay, that's 634. Again, that's not my answer. That is c squared. So to find the answer, we need to take the square root of both sides. The square root of 634 is 25.18 newtons. Okay, that would be the magnitude of my net force. Okay, so that's really only part of the answer because forces are vectors. Now, in my open math, I can't remember, that might be your whole answer. Okay, but forces are vectors and they need a direction. Okay, and so I need to include some directions here. This was talking about a baseball being hit, and so we have kind of left, right, up and down, or forward, backward, up and down, if you will. But we need to define the direction because it's obviously not going directly forward or directly down. It's going a little bit of both. Okay, and so we need to add in some directions. I'm going to just use up, down, left, and right, but I'm going to add in basically an x and a y axis. Okay, and in order for me to really define the direction of this vector, I need to use an angle. Okay, and so in order for me to do that, we're going to find the angle from the nearest axis. Now, this is not drawn to scale. Obviously, this red vector is much shorter than this one, so my nearest is going to be right here, this angle here, theta. Okay, but we're going to determine at what angle it is below that rightward horizontal line. Okay, and so we're going to solve for theta. And in order for me to find an angle, we're going to have to use trig. Okay, so if you are currently in pre-cal, this is probably very fresh on your mind. If you are currently in Algebra 2, you're going to have to think back to last year. If you're currently in geometry, I don't know if you've seen this before, so you really need to listen up. Okay, because you need to know how to do this. And it comes back to this acronym that they teach you in your math class, SOHCAHTOA. Okay, And this is going to help us remember how to solve for sine, cosine, tangent of any given angle based on the information that you have. And so we're going to have to use that here. Now I actually happen to know all three sides, so that gives me a lot more flexibility in terms of how I choose to solve this. But if you don't remember what SOHCAHTOA means, again, this is just a mnemonic device to help us remember the equations for solving for these angles. So the SO in SOHCAHTOA is sine of the angle whatever, theta, equals opposite over hypotenuse. That's the O and the H. In my triangle, that's this red one and this green one. Okay, and this one is color coded too. I think it's the same, but my angle's in a different spot. But that's the SO. The CA in SOHCAHTOA is cosine of the angle theta is adjacent. That's the A over hypotenuse. There's your H. So SOH, CAH, and then tangent, TOA, TOA. Okay, tangent of theta is opposite over adjacent. So again, this should not be new to you, hopefully. Okay, now if you're in geometry, this is probably new to you. And you definitely need to write it down. Or come back to this slide later, slide 22. So in order for us to find theta, we have to use one of these. Now, sometimes we only know two sides of the triangle, but right now I actually know all three. So I could use sine or cosine or tangent, and any of them would work. However, okay, I'm going to go ahead and use tangent, and the reason I'm doing that isn't because it's the right way. It's because it is going to eliminate rounding error for me. I would prefer not to use 25.18 because it's a rounded value. Okay, now if you're using the value as it is in the calculator with all the digits, you'll be fine. But if you're going to use the one on my screen, I wouldn't use this because it's going to introduce rounding error into your answer, and you guys know what happens when you do that in MyOpenMath. Okay, so I'm going to use tangent because that allows me to use the 25 and the 3, and those are not rounded. Okay, so the other thing is, before you do this, your calculator has to be in degree mode. These default to radians. Now, you may have one that's already in degrees because I had my last period do this, but I'm going to show you guys how to change this into degree mode. By the way, you can tell what mode it's in if you look up by the upper right-hand side by the battery indicator. Mine says DEG right now because I'm in degrees. If yours says RAD, then it's in radians. But you might want to just follow along anyway so you know how to do this, just in case you end up with a different calculator later on. So if you're trying to turn your calculator into degree mode, you're going to want to click the dock button, DOC, that's underneath the on button. It's toward the right-hand side, upper right-hand side of the calculator. So click dock, and then option 7 says settings and status, and you can either scroll down to it or you can just push the 7. And then from the settings and status menu, you're going to select document settings. That's option 2. Okay, so when you're on this screen, which by the way is how we made it stop displaying fractions as well. When you're on this screen, the first option says display digits. The second option says angle. That's the one you want to change. Okay, that angle, if it says radians, you need to change it to degrees. Okay, if it already says degrees, you're good. But if it says radians, you need to go to that second option and you need to change it so that it says degrees. Okay, and then after you've done that, you're going to go down to the bottom and click OK to actually set it up. Okay, so make sure you click OK on that screen, and again, you can scroll with the little mouse pad or use the up and down arrows. But please make sure you're in degree mode, otherwise you're about to get every single answer wrong. Okay, so double check it. All right, so tangent, if you need help getting it set up, again, let me just remind you, dock, the dock button, and then 7, and then 2, and then change it from there.
So fast for directions that are degree answers.
I'm about to go through it. All right, so this is now what I'm doing. Tangent of the angle theta equals opposite over adjacent. Again, that's the TOA and SOHCAHTOA. The opposite side of my triangle, opposite my angle theta, is the 3. The adjacent side to this angle is 25. Again, this blue side is the hypotenuse. I don't use that if I'm using tangent. Okay, it's just opposite over adjacent. So I have tangent of the angle theta equals 3 over 25. Okay, now I'm actually trying to solve for theta. Okay, I don't have the angle already, and if you want to solve for the angle, you can't use the tangent button in the calculator. Rather, you have to use inverse tangent or arctangent in your calculator. Okay, so this is how it gets entered in the calculator if you're solving for an angle. Okay, so let me show you where that is on the TI Nspire, because you guys probably aren't super familiar with it. There is a button that says trig next to the number 7. Okay, so find it, and you're going to press that trig button next to the number 7. It's going to open up a menu with sine, cosine, tangent, cosecant, secant, cotangent. It has all of them in here, and then it also has all the inverses. Okay, so you're going to select inverse tangent. It's the third one over, and then the bottom row for the inverse. Okay, and then you can type in 3 divided by 25 inside those parentheses, and when you do that and press enter, if you're in degree mode, you should get 6.84 degrees. If you're not in degree mode, I don't know what you get if you're in radians. Okay, but that's what you should get if you're in degree mode, 6.84 degrees. Does anybody have a question so far about how I got that number? Okay, so we're not quite finished yet, because 6.84 degrees doesn't mean anything if I don't specify what I'm measuring from. 6.84 degrees from what? Okay, I can see it in the picture, but we are going to want to make sure we write it in our answer as well. To specify direction, you must define your reference. What am I measuring from? In this case, I'm measuring from this horizontal to the right. Okay, and so I could say that it is straight to the right, which it's not. I could say that it's above the horizontal, which it's not, or below. I'm obviously below the horizontal axis here, and so when I give my answer, it's not just 6.84 degrees, but 6.84 degrees below the horizontal, so that I know that it's downward instead of upward. Okay, so to give your full answer, it looks like this. The net force, because that's what it said, find net force, is 25.18 newtons to the right at 6.84 degrees below the horizontal. It's a lot of information. Okay, but I have now given you both a magnitude and a direction, and you should know exactly, where that is going. Questions about the warm-up? Okay. We're going to do another one. Okay, so similar type of process. Draw this one out if you want to have another one in your notes. It says, find the net force. This time I have two forces. One of them is 6 newtons, one of them is 9 newtons, and you can see how they are drawn from my object here. It's the same process. Again, if I want to find the net force, I have to start by adding the vectors head to tail. I can't leave them like this. I either have to slide this red vector over here so that it's lined up with the head of this arrow that's green, or I need to slide the green one up so that it lines up here. Either way, you're going to get the same hypotenuse, but I'm going to go ahead and do that and draw that in. Okay, if you had done it the other way, you would just have your vectors here and here instead. It would give you the exact same hypotenuse. All right, so we're going to find the net force. Again, that is going to be this blue resultant vector that I've drawn in, and we're going to solve it with Pythagorean theorem, same as we did in the warm-up. A squared plus b squared equals c squared. This time I've got 9 and 6 as the legs of my right triangle, so that's 9 squared plus 6 squared, or 81 plus 36, which is 117. Again, this is not your answer. You need to take the square root of both sides, and the square root of 117 is 10.82 newtons. So this is the magnitude of your net force, 10.82 newtons. This is not your whole answer. Forces are vectors. Vectors need a direction. Okay, so again, we need to define the direction. I showed you last time how to define it with just above or below the horizontal. This time we're going to define our direction using cardinal directions, because the question might not be a baseball. It might be there's a force north and a force east. Okay, we could have it like that. So let's go ahead and do this one, and so I can show you just one more way that you can define your direction. Similar process though. So I added in north, south, east, and west. Okay, and my angle that I'm solving for, we're going to do it from the east axis because I already have a vector on this axis. So we're going to do my angle here. Okay, but we're going to be measuring in degrees from this eastward axis. And again, we're going to go back to SOHCAHTOA. We know all three sides of our triangle, so we could technically use sine or cosine or tangent, but again, this 10.82, my hypotenuse is a rounded value, so to avoid any rounding error, I'm going to use tangent again. If you use the other one, it's fine, just I would use the entire value from the calculator. Yes, sir?
Can you always use tangent?
If you know both of the legs of the triangle, yeah, tangent's a pretty safe bet. Again, have to be in degrees. Tangent of theta equals opposite over adjacent. That's the O and the A in TOA. That's 6 over 9. But again, to type it in the calculator, since we're solving for theta, inverse tangent or arctangent, 6 divided by 9. When you type that in and press enter, you get this angle, 33.69 degrees. I know this isn't math class, guys, but unfortunately, or maybe fortunately if you love math, but for some of you, unfortunately for you, physics oftentimes looks a lot like math because it's basically applied math is what we're doing. So we're going to see a lot of crossover here. 33.69 degrees. All right, again, that's not enough information. I need to describe degrees from where? 33.69 degrees from where? And we're going to define it from the east axis. So that means I can say that I have 33.6, my force rather is 10.82. 10.82 newtons due east. If it was straight to the right, that's all I would do. Again, this is not, so we're not going to do that. Okay, so it's not due east. Rather, we're either going to be north of east, meaning we're above the east axis, or we're going to be south of east, meaning we're below that east axis. Obviously, the way this is drawn, we are north of east, and so that's how you're going to define the direction. 33.69 degrees north of the east axis, or you can just say north of east. Okay, so again, my total final answer for net force, if I put it all together, looks like this. The net force is 10.82 newtons at 33.69 degrees north of east. That is how you would write it. Okay, again, you're just finding the angle with respect to the east axis. Questions about this one? Because ultimately, this is not the whole problem. The whole problem is going to be when we take this and we say, hey, now we're pulling something at an angle, or we're pushing something at an angle, and you're going to do the whole calculation with a force applied at an angle, but you have to do this piece of it within the rest of the calculation. Okay, so it's going to become a lengthy problem if you have a force at an angle. That's why I'm strongly suggesting that you copy down some notes to look back at so that you have them in case you get stuck. Because this is some of the trickiest stuff that we have in here. We'll have it again in projectile motion, but all right. Let's try a problem that's not at an angle first. In fact, you've done this problem before because I gave it to you in the last unit. Maybe you already have it copied down because it's this ridiculous guy dragging this ridiculous ice cube. Okay, maybe you already have this copied down, but if you want to copy it down again, you can, because we're going to take this, we're going to work through one that's not at an angle, and then we're going to do a similar process when it is at an angle so you guys can see the difference. All right, so this problem says a large block of ice is being pulled to the right across a frozen lake. The block of ice has a mass of 250 kilograms. The coefficient between the two ice surfaces is small. Mu is 0.05. What is the force of friction acting on the block of ice? Okay, so we have some information given to us, a mass and a coefficient of friction, but that's pretty much it. So if I want to solve for the force of friction, I know that I can use that coefficient of friction times my normal force to find force of friction, but I don't know what my normal force is until I draw my free body diagram. So again, good first step is to start with that diagram. So I'm going to draw my diagram, and it's going to look something like this. I have my ice block, I have my force of tension because he was pulling it with a rope, I have the weight, the force of gravity pulling on that ice block, I have the normal force from the surface, and I have my force of friction. Okay, so looking at this, again, ultimately I'm trying to find the force of friction, which means I need to find normal force. And although I don't have an equation for normal force, I know that this block of ice has 0 vertical acceleration. It's being pulled horizontally. It's not being thrown upward or something like that. And so I know that Fn and Fg will have the same magnitude. So if I solve for Fg, which I do have an equation for, Fg is mass times gravitational acceleration. That will give me Fn and Fg. 250 times 9.8. Technically it's negative for weight, but again, I'm just looking for the magnitude since they're going to be equal and opposite to each other. So that's 2450. So that's both Fn, positive 2450, and Fg, negative 2450. They're going to have the same value, just opposite signs. So that is my normal force, and so I can use that to solve for force of friction. Mu, 0.05 times Fn, 2450, gives me a force of friction of 122.5 newtons. Notice I added a negative sign because if I look at my diagram, it's to the left. I'm going to go ahead and call that the negative direction. Okay, you don't get a negative number, you just have to look at your picture. So, force of friction. Again, we worked through this problem before. You probably already have it in your notes. In fact, there was a couple other pieces to it. So let's finish out the problem. Now we know that the acceleration of the ice block is positive 2.5 meters per second squared. You'll notice I added all the numbers to the picture. And we've got a couple other questions to answer just to finish this process. And this is what you were doing on the last test. In fact, your short answer question looked a lot like this one. Okay, what is the net force on the ice block? Again, net force, I could find it if I had all the forces in my diagram. I could actually find it that way, but I don't. So the other way you can find net force is with the net force equation, F net equals m times a, where you do mass times acceleration, and I do have that information. They're both in the question. That's 250 times 2.5, and that gives me a net force of 625 newtons, and it's positive or to the right. Okay, so there's my net force. The last question is, what is the tension pulling on the ice block? So I'm going to add my net force over here, and now I'm going to solve for this piece. And again, I don't have an equation for tension, but I do know net force isn't just equal to ma, it's also the sum of my forces. By definition, the net force is also equal to my forces to the right plus my forces to the left. And I only have a net force horizontally, so that's why I didn't write out the vertical one, because that's 0. Okay, but net force in the x direction we just found to be 625 newtons to the right. My rightward force, Ft, I don't know what that is. My leftward force, again, forces are vectors. Make sure you put that negative sign on, negative 122.5. I'm going to solve for Ft. Right now, I'm basically subtracting 122.5 on the right, so I'm going to add 122.5 to both sides to cancel that. 625 plus 122.5 gives me a force of tension of 747.5 newtons to the right. Okay, again, this process should hopefully seem very familiar and comfortable to you. You guys did pretty well on the last test, so I'm assuming most of you have this stuff down. Maybe you haven't looked at it in a while, but you should have it down. Okay, and if your object is being pulled horizontally, it's this straightforward. If it's not, which is what we're about to look at, what if it's pulled at an angle? Let's work through this problem because there are going to be some additional steps here. Okay, and they're similar to what we did in the warm-up. This time it says a block of ice is being pulled to the right across a frictionless surface with a force of 183 newtons at an angle of 25 degrees above the ground. If the block has a mass of 40 kilograms, find its acceleration along the surface. This time we have a picture so we can see exactly where that angle is, but it's also described in the question. He's pulling to the right at an angle of 25 degrees above the ground. Hopefully that's what you pictured in your head as well. Okay, so we're ultimately looking for the acceleration along the surface. But in order for me to solve for acceleration, I have to have net force, and in order for me to get that, I'm going to need a diagram. So let's draw all of the forces acting on this ice block. A great place to start, Fg. We know we're always going to have force of gravity, okay, as long as we're on Earth or some kind of planetary body. Okay, the other force that's described in the question is him pulling this at an angle. So I'm going to draw it at an angle in my picture. And I'm going to draw it at an angle of 25 degrees above the horizontal. If you want to draw in an x and a y axis through the center of your object, then you can see how that might look. Or you can just draw what I have here, 25 degrees above the horizontal. So I drew in a horizontal axis. That's my dotted line. There's my 25 degrees. And here's my 183 newtons. Okay, the other force that I have here is from the surface pushing upward. That's my normal force. Okay, and so I'm going to add Fn in the upward direction. Now you might notice, looking at my picture, that I drew Fn a little shorter than normal. And the reason I drew Fn a little shorter than normal is because, is this ice block accelerating vertically? No, he's just pulling it across the surface. My vertical net force still has to be 0, but now I have 3 vertical forces. Because he's pulling it at an angle, a portion of his force is upward. That portion of his force will add with Fn, and it will still together equal Fg. Okay, but we're going to have to solve for that portion so you can figure out exactly how long to draw that arrow. I don't know how long, I just drew it a little shorter than Fg. Okay, so again, if you have, by the way, those are my only forces because it says frictionless. If it had said there was friction, this problem is actually a lot harder. So we're going to start with the easier one. No friction, yes.
Are you explaining it why the normal force is a smaller arrow?
We're going to get to it when we get to the math, but whenever you pull something at an angle, part of this force is to the right and part of it is up. And because part of it is up, this upward piece will add with this to equal the same magnitude as Fg.
When it pulls it at an angle, it's not going to lift it up?
No. If you pull something at an angle,
I thought it would lift up.
I'm not lifting this right now, but I'm pulling at an angle. Okay? He's not lifting it. He is just dragging it across the surface. If you've ever like pulled a wagon or something, same thing. You're pulling at an angle, but you don't lift the wagon up. Okay. I mean, you could, I guess, if you yanked it really hard, but he's not doing that. All right. Again, no friction to include, so that's it for my diagram. But if you have any forces at an angle, and this is always the case, if you ever have a force at an angle, you need to determine the horizontal and vertical components of that force. We can't leave it at an angle when we do our calculations. We have to figure out how much of that 183 newtons is sideways and how much of it is up and down. Okay, and so now we have to draw a triangle like this one, and we have to solve for the force of tension in the x direction and the force of tension in the y direction. And this is somewhat similar to what I showed you in the warm-up. It's not the same though. Okay, because this time I gave you a side and an angle rather than giving you 2 sides. Okay, so now we have to use trig. You don't have an option. Okay, so draw this triangle out, and you can draw it here if you want. I just added it over here to the side, so I had some room to work. But here's my 183 newtons, and here's the x component and the y component of that force. Let's start with the x component. If I want to solve for this purple vector, my x component of the force, I have to use cosine, because that is adjacent to my angle, and cosine is adjacent over hypotenuse. Okay, so that is cosine of theta, 25 degrees, I know the angle this time, equals the adjacent side, ft in the x direction, divided by the hypotenuse, 183. Okay, and so if you have that, you're just going to multiply both sides by 183, and you're going to have 183 times cosine 25, and that's how you're going to get your answer. If I were you, I would make sure that you can type that in your calculator, okay? Make sure you know where all the buttons are. But 183 times cosine 25 is equal to 165.85 newtons. Okay, I added it to my diagram, so it's down there at the bottom. 165.85 newtons. We're going to do a similar process to solve for the force in the y direction, except in the y direction, that is now opposite my angle. Okay, and I actually know 2 sides. I know both the hypotenuse and the adjacent side, so I do have some options here, but I'm going to go ahead and use sine. I'm not going to use that rounded value. I'm going to use the one that's not rounded, my hypotenuse. And I'm going to say that sine of 25 degrees is opposite over hypotenuse. So f in the y direction, ft in the y direction, divided by 183. Again, multiply both sides by 183, and that's 183 times sine 25. And when you multiply that out, if you're in degree mode, you get 77.34 newtons. Okay, so now I have both the components. That's going to be basically step 1 if you have a force at an angle. After you draw the diagram, do that. Before I go any further, does anybody have any questions about how we got these values? Okay. So I now have my x and y components. Those are the things I need to use to solve. I don't need 183 newtons at all. I only needed it to find the pieces. Okay, so I don't need this red vector in my diagram anymore. So we're going to take it out of our diagram, and instead we're going to add in the pieces that make it up. Here's that purple piece, here's the gray piece. Okay, notice I now have two forces in the upward direction. So Katie, that's what I was talking about. They're both going up now. Okay, so I have both Fy, or Fty, and Fn going up. I have Fg going down, and I have the x component of that 183 newtons. This is the amount that was in the horizontal going to the right. So you can just redraw your free body diagram after you find the components. You don't have to, erase or scratch it out. Just draw a second one next to it. Again, before I go any further, does anybody have any questions? Okay. So once you get to this point where you have everything in the horizontal or vertical, again, here are your basic steps for solving a second law problem. So if you're solving a problem using the F equals ma equation, okay, where you're having to do a calculation, your first step is to draw the free body diagram and break into components. We already did that step. Okay, so if you have it at an angle, break it into the components, find the x and the y pieces, okay, because you can only have forces in the x and the y. Okay, so second step after you've done that, okay, so that's where we're at now, step 2, determine F net x and F net y. Again, we need to see what our net force is in the x direction, what our net force is in the y direction. Again, vertically, this block of ice isn't moving vertically. It's just being pulled across the ice. Okay, so my vertical net forces are going to be 0. But horizontally, I can see my net force horizontally. There's only one. Okay, so my net force horizontally is 165.85 newtons to the right, because that's the only force in the horizontal direction. Now, if I had friction, that'd be different. That's why I said it's harder if we add in friction. Okay, and then you can find acceleration in the x and y. So again, in the y direction, I need these to be equal and opposite. Fn plus Fy together need to be equal and opposite to Fg. Because vertically, I need 0 net force because this object isn't accelerating vertically. So F net y needs to be 0. The forces must balance. There's no mention of any vertical motion or acceleration. F net x is 165.85 newtons to the right because it's the only horizontal force that's there. This is the x component of the force of tension from the question. Yes, sir?
On that triangle thing, when you used the trig, did you even have to solve for the y?
You have to, I did not have to solve for the y in this question. However, if the question had said that there was friction and it said the coefficient of friction between the two ice surfaces is 0.15, then you have to solve for the y so that you can get Fn, so that you can find the force of friction, so that you can find the net force, so that you can find the acceleration. It adds in like 3 extra steps. That's why I said if there's friction here, it is more work. We're going to do the easier one first without friction. But yes, I would solve for the y component. You don't. In this case, we don't have to, but I would do it if for sure you have to if there's friction. Or if the question asks you for the normal force, you would have to as well. All right. So again, the question is find the acceleration along the surface. F net x is the only direction where I'm going to have acceleration is in the x direction. Okay, so F net x equals m times ax. Again, if I had anything in the y, I would do this again in the y. I don't have it, it's going to be 0. Okay, but F net x equals mass times acceleration in the x. That's the only direction where I'm going to have any acceleration. So plugging in my numbers, I have 165.854. Here's more digits if you want to be more precise with it. Equals the mass from the question is 40 times a. Divide both sides by 40 to get a by itself. And that gives me an acceleration of 4.146 meters per second squared to the right. Again, it's in the same direction as my net force, which is to the right. Sorry? Oh, I was dividing both sides by 40 to cancel. Other questions about how I got this? You're going to be doing problems like this in your assignment today. Some of them might have friction as well. I would hold off on those because your assignment is not due till tomorrow. Okay, so for the rest of the class period, I would open up 401.2, two-dimensional second law problem set. It's due tomorrow night, not tonight, tomorrow night by 11:59 p.m. But I would try some of them. You can do some of them today, I promise. Okay, like the first one, and some of them aren't even at an angle, so you can definitely do those. You can get a bunch of these knocked out, but if you're not super comfortable with all the stuff at an angle yet, you might want to hold off on some of the questions till tomorrow because it's not due tonight. Okay, but go ahead and get it opened up. If you have any questions or need any help, ask me, ask your neighbor, but make sure that you get started on it so you don't have, all of it to do tomorrow. Again, get to work. Let me know if you have any questions.